We've made it to related rates. Okay, gonna be real heavy on word problems today when we work these related rates. I'm gonna try something. I'm gonna try to minimize that. Oh great, I don't know where that went. So hopefully this will still record. All right, so it says in a related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity. So we're going to have two quantities that are changing changing values. We're going to be doing rates of change of two quantities at one time. I know like in the first example we're going to do how fast the volume is changing and how fast the radius is changing of a sphere. Okay, so you're going to have to use a chain rule. It's going to look a lot like implicit differentiation as well. Probably the hardest part of this, though, is being able to come up with your equation. Okay, if they don't give it to you. I think I've assigned some where they do give it to you. So it says air is being pumped into a spherical balloon so that its volume increases at 100 centimeters cubed per second. Okay, so I'm just going to draw me a balloon here, put a little string on it. And so air is going into the balloon, so this balloon is getting bigger at this rate, 100 centimeters cubed per second. I want to know how fast the radius of the balloon is increasing, because if the balloon's getting bigger, I know the radius is getting bigger, whenever the diameter all the way across is 50 centimeters. A lot of people say, well, the answer is 25. I want to know how fast the radius is changing. I don't want to know how long the radius is. I want to know how fast the radius is changing. Okay, so I'm going to need to use my volume of a sphere. Let's see, that's 4/3 pi r cubed. Got that from my geometry teacher when we did 3D objects. So we'll actually derive where that comes from in a later video. It's a good video. And so the whole idea with a related rate is I've got both my volume is changing in this problem and my radius is changing in this problem. So when my volume's changing, it's changing with respect to time. I know that because as time goes on, that's what's making this get bigger. Okay, and so I'm gonna write this out once for us. I probably won't do it every time, but I'm wanting to take the derivative with respect to r, because that's what my volume is in terms of. But ideally, if I take the derivative of r, I need to take it with respect to t, because if I cancel my dr's right here, then I'm just left back with dv over dt. And so that's kind of the math as to why this works. So let's plug in what we know. dv over dt. I'll actually plug that in a minute. I'm going to go ahead and take the derivative of my v with respect to r. So if I drop the 3 down in front, 4/3 times 3 just gives me 4. And then I lower the exponent by 1. Pi is just a very much like my implicit differentiation from a couple weeks back. I'm going to solve this a little bit different than the book. I'm looking at my notes and I'd rather do it a tad bit different. Now I'm going to plug in what I know. I know the volume is increasing at 100 centimeters cubed per second. That 100 is going to go in right here. Now I can plug in my r. I have a lot of people want to plug in the r up here, but remember, r is changing. So I need to take the derivative of r. I can't plug in for r until the bottom. So if the diameter is 50, my radius is simply going to be 25 squared. And if you were in class, I'd be grilling you right now. dr over dt, what are we going to plug in for it? Well, that's what we're trying to find out. How fast is the radius of the balloon increasing? That's what I'm solving for. So make sure you're solving for one of your rates of change. And so if I just divide both sides by, 25 squared, that's something really big. Hold on. If I divide both sides by 4, it gives me 25 over, and then divide both sides by 25 squared pi. The 25's cancel. I'm left with 1 over 25 pi for an exact answer. That's going to equal my dr over dt. Let's throw some units on there. So we're talking about the radius. The radius is being measured in centimeters, and then over time, time is in seconds. So the radius of the balloon is slowly increasing by 1 over 25 pi centimeters every second. It's a good geometry one. We'll come back and do another geometry one. Actually, this one I think is going to be geometry as well. Santa is on top. Oh, we still got some squiggles, don't we? Santa is on top of a ladder that is 10 foot long, and it rests against a vertical wall in an attempt to reach the chimney. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is Santa sliding down the wall when the bottom of the ladder is 6 feet from the wall? Let's do wall, let's do ground, and then we'll do ladder. Okay. Now I just kind of drew it. I didn't really pay attention to it, but one thing's not changing on this is that 10. Okay. Whether the ladder is all the way up or all the way down, that ladder is going to be 10 foot tall if it's all the way up against the wall or if it's lying on the ground. Let's see, what else do I know? I'm eventually going to know that x equals 6 down here, but that's not a constant. Not a constant, because as the bottom of the ladder is sliding away from the wall, 6 is going to get bigger and bigger and bigger. I'm just taking an instantaneous snapshot as to what's going on when it's 6 foot from the wall. And it says the bottom of the ladder slides away at 1 foot per second. So how fast this x is changing with respect to time is 1. So I'm wondering how fast this ladder is going down the wall. I'll just, since that's going in the y direction, we'll call that dy over dt. That's what I'm looking for. Okay. Well, I have a nice right triangle right here, and I'm pretty sure whenever I have a right triangle, the way that the three sides relate to each other is that x squared plus y squared equals r squared. Or r squared. We used r last year. A squared plus b squared equals c squared. That one will work too. Let me do that one. Nope, I want to do x's and y's. If you guys can't tell, I really thought this problem through. I'll just use r. You can use c. You can use whatever you want to, because my hypotenuse, like I said, it is always going to be 10 right there. Always. Okay, it's not changing. How far the bottom of the ladder is from the wall and how far the top of the ladder is off the ground, that is what is changing. So I should be able to take a derivative of this now. And again, the only thing I plugged in was my r, because it was constant. X and y are both changing because the ladder's sliding down the wall. So the derivative of x, but then x is changing. I'm taking the derivative with respect to time here. So like I said, it looks very implicit. And the derivative of 10 squared is going to be 0. Derivative of 100 is just a constant. So let's plug in what I know. I know that x is 2. I'm sorry, I know that x is 6. That's going to be 12. And then dx over dt is how fast it's sliding away from the wall. My y, now this is where I'm just taking that snapshot. My y actually can be plugged in with the 6 and the 10 into this equation right here. 6 squared plus y squared equals 10 squared. Okay, and so that gives me y squared equals 64? 36, 64, yeah. And then y equals plus or minus 8.
At this time, the band members that are participating in class out may be released to go return. Thank you.
All right, all sorts of interruptions today. So whenever the bottom of the ladder is 6 foot from the wall, 6 foot from the wall, the top of the ladder is 8 foot up the wall, thanks to my Pythagorean theorem. And so this is going to be 2 times 8. And then dy over dt. Oh yeah, that's what I'm looking for. So I'm just going to leave it, dy over dt. So what we got here? We've got a 12, we've got a 16, we have a dy over dt equal to 0. So if I subtract 12 from both sides, and then divide both sides by 16, let's see, that'd be negative 12 over 16, divide out of 4, negative 3/4. Negative 3/4 what? Well, the ladder is in feet, and it's sliding away. We're measuring it in seconds. So the ladder, the top of the ladder, while the bottom of the ladder is moving 1 foot per second, the top of the ladder is sliding down at negative 3/4 foot per second. And it's negative because it is moving in a negative direction going down. So I do like to see that negative in there. Or you can just wrap it up with a sentence. You can just say ladder, the ladder is sliding down the wall at 3/4 or 0.75 feet per second. Awesome. I think I'm going to work all these for you. These are tougher problems, so we're not going to pause the video any today to work some out. If you want to, you can just jump ahead if you want to, because this is another geometry problem. It's talking about us having a water tank that has the shape of an inverted circular cone. So that's one of those water tanks that look like that, where the water kind of comes down this way. With a base radius of 2 meters, that's kind of a misnomer. Base radius is going to be up here at the top, and a height of 4. So the height of the whole thing is going to be 4 meters. If water is being pumped into the tank at a rate of 2 meters per minute, find the rate at which the water level is rising when the water is 3 meters deep. Okay, so one of my variable here is going to be when this is 3. So I've got to take the derivative, and I'm going to have to plug in 3 after I take the derivative of it. Okay. Now, does anybody happen to remember something that's bothering me? This should be 2 meters, or this is volume right here, 2 meters cubed per minute. There we go. All right, does anybody remember their volume of an inverted circular cone from geometry? I know I wouldn't, so I probably would give you this formula if you're needing to know it. 1/3 pi r squared times the height. Well, I have too many variables on this one. I just want 2 variables on these related rates. I got volume, I got the volume is changing, I got the radius is changing, and I got the height is changing. Okay, so that's way too many. So what I'm going to do is I'm going to need to get rid of a variable. Okay, doesn't matter which one. But this r and h right here, I just need to have either r or h, not both. Well, if I do a quick ratio here of my radius over height, it's going to be 2 over 4, which is just 1 height, meaning that my ratio of radius over height is 1 height. Or multiply both sides by h, that my radius is simply going to be always half of my height, no matter where I'm at on this cone. That makes sense, because the radius of the whole cone was 2, and then the height was 4. And so it's always going to have that same proportion as I work my way down the cone. So what that's going to allow me to do is rewrite my volume 1/3 pi r squared. Oh, I'm going to do it in terms of h. 1/3. Instead of r, I'm going to write h over 2 squared times h. So I just took out my r and put in h over 2. because my radius is going to be whatever the height is divided by 2, anywhere on the cone. I can clean this up some now. So it's going to be 1/3 pi h squared over 4h. Well, that would be 1/12 pi h cubed. I'm trying to make it so when I do my calculus on here, I'm just having to use the simplest differentiation rule I can. So I'm still taking the derivative of this with respect to time. So how fast the water volume is changing with respect to time. Let's see, drop the 3 in front. 3 times 1/12 is 1/4 pi r squared times the height over t. Another reason, it says find the rate at which the water level is rising. That is the height of my water. So that's another reason to leave h in the equation and substitute in for r. So now I am just going to substitute in what I know. I know that water is being pumped in at 2 meters per second. Isn't that right? I worked it different in my notes. We're just going to go with it. Water's being pumped in at 2 meters per second. And then I got 1/4 pi. And then I'm wanting to know the level of the water when the water is 3 meters deep. So that's my snapshot. That's my instantaneous height that I want to find the rate for. So if I plug in 3 into the h, that gives me a 9. And then I still have my dH over dt that I'm looking for. So that gives me 9/4 pi. So that would just be, or we can just multiply both sides by 4 first. I think that might be a little bit easier to see. So my exact answer is going to be 8 over 9 pi for my dH over dt. Okay, and then the units on this would be in the meters per minute. Meters per minute, because that's what I measured height in, and then that's what I measured time in. Okay, so the water is rising at this rate. So a little bit of substitution on there, but I don't think it's anything just terribly new that's going to be hard for you to work through. Oh, Lightning McQueen. Are you guys too young to remember Lightning McQueen? I don't know. Might have been between our ages. I know I think my middle school son liked him. So Lightning McQueen's traveling west at 50 miles an hour. Okay, I'm going to let this be west. 50 miles an hour. Since that's in the x direction, I'm just going to say x. I'm going to say my dx over time is 50 miles per hour. Okay. And Jimmy Johnson is traveling north. Oh, I picked a terrible spot for that, didn't I? So let's bring him down. All right. So Jimmy here is traveling north that way. And how fast is he going? 60 miles an hour. And so that would be my dy over dt. I just chose y because that's up and down. I need to pull him out so he's not going to be in my triangle here in a minute. Oh, and they're both headed for an intersection. I am just striking out on this. I mean, maybe I should just redo this whole thing. Maybe it's good that I make mistakes. I don't know. There we go. They're heading towards this intersection. Really? Really? There we go. I feel good about this now, other than the fact that it doesn't fit on there. Okay. So they're both headed towards this intersection. At what rate are the cars approaching each other when Lightning McQueen, see Lightning is the bottom one, he is going to be 0.3 miles out, and Jimmy is 0.4 miles out from the intersection. So I'm just wondering, there's this imaginary line that's joining the two cars right here. And so as I get closer to this intersection, that blue line is going to be decreasing. So hopefully that might get a negative answer to show that that blue line is decreasing. But I'm just wondering how fast that blue line is going to decrease. Let's see if I can get my variables right this time. Okay, I still got the right triangle, so I'm still going to have x squared plus y squared. I'm going to call it z squared. Okay, I don't know how long z is. I could find it, but first I need to do my calculus with it. I'm going to take the derivative of each one of these variables because they're all changing with respect to time. Okay, so it's going to be 2x dx over dt plus dy over dy dt. And that's going to be 2z dz over dt. So now I can plug in what I know now that I've done the rate of change on everything. So my x is this 0.3. That's my snapshot. 2 times 0.3, I'm going to call that 0.6. Oh, and I know how fast lightning's going. Lightning's going 50 miles an hour. Okay. 2 times y. My y is 0.4, so I'm going to call that 0.8. And Jimmy's going 60 miles an hour. And then my z. Well, if this is a true right triangle, it's just going to be a 3, 4, 5 triangle. So whenever Lightning McQueen is a 3/10 of a mile out and Jimmy is 4/10 of a mile out, that means that the distance between them has to be half a mile or 5/10 of a mile because it's a 3, 4, 5 triangle. And so if I double that, that's just going to be 1 dz over dt. Hey, I've already got it solved for dz over dt. Now, the answer that we get on this whenever I finally do it is 78 miles per hour. That's my dz over dt. I told you earlier that answer is going to be negative. But if you want to just wrap something up and say that the two cars are heading toward each other at 78 miles per hour, full credit. The reason we didn't get to be negative is that since they're heading towards each other, I'm supposed to throw negative signs on those. And that gives me a negative 78 miles per hour. Again, I'm not really interested in whether you're telling me it's positive or negative, but wrap it up with a sentence that explains what's going on. Pretty much you're restating the last sentence that you see in the problem. At what rate are the cars approaching each other? The two cars are heading toward each other at 78 miles per hour. Okay. So whether you get positive or negative on that, I'm not going to be a big stickler about it. Whew, we got one more. The band's going to be coming through in just a little bit, so hopefully I can beat them. Got a clap out today. So Martha Stewart, she went to jail a while back. Not making fun of her, but just had this picture, I guess. And evidently she escaped jail and started walking away because I can't imagine Martha Stewart running, along a straight path at a speed of 4 feet per second. Okay. Here's Martha. I need to move her up a little bit. So let's put Martha up here. Here's Martha. She's walking this way. And her speed, I'm going to call that dx over dt, is going to be 4 feet per second. Now, there's a searchlight that is located on the ground that's 20 feet from her path. My searchlight looks a lot like a sun, but it'll be okay. That searchlight is 20 feet from the path that she is walking on. So at what rate is the searchlight rotating when Martha is 15 feet from the point on her path that is closest to the searchlight? So Martha's made her way all the way over to here. And she is now 15 feet away right here. And my searchlight, boom, is right there on her. I want to know how fast this angle is rotating. You're right, I still do have a right angle happening right here. It is, but I'm not interested in how long the ray of that searchlight is. I'm interested in its angle. And so look at the angle I'm given right here. And look at the two sides I have, opposite and adjacent. Do we have one of our trig functions that deals with opposite and adjacent? I hope you said tangent does. Tangent of that angle is going to be the opposite side, which is going to be my x, over adjacent. Okay. Now, I do need to take a look at this as to what's going to be constant on here. The 20 is going to be constant. This spotlight right here is not moving. The adjacent side is always going to be 20. And then the opposite side, this 15, well, Martha is moving around. She's trying to get away. So this 15 is not constant. It varies as to where she's at on this line. It's kind of fun just moving her back and forth like that. So that's going to be my x. And I'll be able to plug in for it once I take the derivative. She's going to talk while I do this. It's going to be kind of weird.
Good afternoon. This is Blake Carrillo. This past Saturday, we had 3 runners qualify for the state cross-country meet that will be held tomorrow in Columbia. Congratulations to the freshman Abby Lloyd and to junior Gabby Brown.
So I'm running really short on time. All right, so I'm ready to take the derivative of this. Almost ready, actually, because I'm going to get rid of that fraction. It's going to help me if I call that 20 tangent theta equals my x. So now I can take the derivative of both sides. Derivative of 20 tangent theta. Well, 20 is just a constant that I can pull out in front. Derivative of tangent is secant squared. And then the derivative of x is 1, so dx over dt. Oh, did I forget something? I'm so worried about these runners coming through. I did take the derivative of the theta. So I'm going to need to solve it for d theta over dt. All right, and I'm going to go ahead and solve it. I'm going to work this one a little bit different. So I'm wanting this d theta over dt by itself. And so that's just going to give me dx dt divided by 20 secant squared theta. And I don't like that secant squared theta on the bottom. So I'm going to bring it to the top and call it cosine squared. Because 1 over secant squared would just be cosine squared. And then I still have my dx over dt. Let's see if I can figure out what everything is going to be from here. 1 over 20. Let's see, cosine squared. Cosine squared of theta. Cosine is going to be the adjacent over the hypotenuse. Well, the adjacent side is 20. The hypotenuse on this, well, if I make it a 3, 4, 5 triangle, or I could do Pythagorean theorem, it would be 25. I've got to square that and then multiply it by dx over dt. There's where the speed of Martha is going to come back in right there at 4. So I just plugged all this in. I got like 16 over 125. And that would be in radians per second. If you wanted to decimal it out, I got 0.128. All right. This is gonna take some practice. I put some in here that are harder than ones in the video. It's gonna make you think. So let's find those. Make sure that you work through it. For some reason, I'm supposed to check the homework. So make sure this matches what's on your Google Classroom for this year. Okay. I will talk to you guys next time. Have a good one.